Okay, it's recording now. Okay, welcome to everyone. Today we have our 10th seminar of this 2022 series of seminar of the Magnetic Resonance Laboratory. In this opportunity, we have a talk from the U.S. That is going to be in charge of Axel Hoffmann. So I will introduce him now. Axel obtained his diploma degree in physics from the RWTH at Chin in 1994. His PhD degree in physics from University of California in San Diego in 1999. Then he worked at the Los Alamos National Laboratory as a postdoc fellow. And in 2001, he joined Argonne National Laboratory as a staff scientist and became, in 2014, senior group leader of the magnetic thin film group. In 2019, he joined the Department of Material Science at the University of Illinois at Urbana-Champaign as a full professor. And his research interests encompass a wide variety of magnetism-related subjects, including basic properties of magnetic aerostructures, spin transport in novel geometries, and biomedical application of magnetism. His main research focus has recently been on pure spin current investigated by magnetotransport and magnetization dynamic measurements. He has more than 2,000 publications, 5 book chapters, 3 magnetism-related U.S. patents, and edited 2 books. His awards include the Distinguished Lecturer for the IEEE Magnetic Society in 2011, Outstanding Researcher Award by the Perry section of the American Vacuum Society in 2015, and he's the president of the International Fellowship from the Chinese Academy of Science in 2016. And recently, in 2022, he got the David Adler Lectureship Award in Material Physics from the American Physical Society. Please, Axel, we are looking forward to hear your talk that is going to be on topological quasiparticle, magnetic Skermion. Please go ahead.
Yeah, thank you, Luis, very much for the introduction and, of course, the invitation. And, of course, it would be even nicer to be there in person, but I'll be there in November, right? So I'm looking very much forward to seeing many of you then directly. So today I want to tell you a little bit about our work on magnetic Skermions that we've done over the last 10-ish years or so. And so here's a brief outline of my talk. I will first discuss in general magnetic Skermions and magnetic multilayers. Then I'll evaluate Skermions electrically. It's kind of seen in this picture here already, where you blow them out of a small constriction. Next, I want to discuss a little bit how the topological properties of Skermions affect their motion. I'll talk about what's known as the Skermion Hall effect. And I'll end with a few brief conclusions. So first, let me step back and in general discuss a little bit what are still new territory to cover in magnetism. I mean, magnetism is probably one of the oldest topics of scientific curiosity in some way. What is there still new to see? What makes magnetism such a fascinating topic is that there are a wide variety of interactions that compete with each other. You have, of course, atomic exchange interactions that act at an atomic level, very short length scales and very fast time scales. But then also, of course, many of us are familiar with the long-range interactions that magnetism is often used for, that comes due to dipolar interactions, which are macroscopic length scales, gives us macroscopic domains and dynamics that can be very, very slow, seconds and even longer. And if you now combine this with all kinds of other interactions like anisotropy, spin-orbit interactions, Zeeman interactions, then this results in a surprisingly rich complex spatial and temporal spin textures. And that's pretty much what drives most of current magnetism topics to this day. And I list here just a few that are interesting for our group. And I'll focus on one in particular here, Skermions, in more detail in this talk. So the other reason why are we looking into the kind of ways how we can manipulate magnetization is the following. As you may know, if you look at current day electronics, the increased miniaturization of electronic devices gave rise to a problem where as you miniaturize the systems more and more and more, the heat dissipation becomes more a problem. And the basic reason for that is that the functionality of the semiconducting devices is typically derived from the electric current that goes to the bulk of the material, while the dissipation is derived by currents that leak out through the surface of the devices. And so by making things smaller and smaller and smaller, it's just unavoidable that the dissipation will become a much bigger problem. And it's one of the major problems in improving semiconducting electronics even further these days. And so one of the questions now is, are there ways how you can things do better? And can you possibly make things better by using the spin degree of the electrons? And so the first thing that you can do is you can think about using spin polarized charge currents, which are depicted here, where instead of having equal numbers of spin up and spin down carrying a current like in a normal conductor, you have a current that has different numbers of spin up and spin down currents. Now you can take this one step further and think about pure spin currents, where now you have the spins, instead of moving in the same direction.
Hello, Axel. Axel, are you in
yes.
slide? Are you on slide 1 still?
No, I'm on slide 4.
Here I can see only the first one. What's still new in magnetism? I think it's stop for some reason.
All right. What do you see now?
The PowerPoint. The PowerPoint. Yes, I see the PowerPoint now, but.
Let me start again.
Yeah.
All right. You see now?
Yes, motivation beyond electronics now.
All right. Sorry for those technical problems.
It's okay. Yeah.
Okay. So I was discussing how we can use possibly spin polarized charge currents, where you have different numbers of spin up and spin down electrons carrying the current. You can go one step further by looking at pure spin currents, where you have spins of different direction moving in different spins of opposite direction moving in opposite directions as well. So in this case, the charge current overall is 0, but you still have a net spin current. And you can take this one step further, and in magnetically ordered systems, you can also propagate spin information through magnetic excitations called spin waves, magnonics. And so the first two suffer from essentially the same dissipation mechanisms as electronic transport to begin with. So it's not clear that in terms of power dissipation and what you necessarily do much better. Here in magnetically ordered systems, you now propagate information very different. You don't move any electrons anymore, so you don't have to be concerned with ohmic losses and things of that nature. And so there's the possibility maybe to do something more energy efficient in a way. And so what I will be talking about today is kind of like a combination of generating pure spin currents, which then manipulate spin textures. So if you want, it's a hybrid version of these two ideas. Skermions. And if you're interested in this, and if you like my talk, there's a more expensive review that we wrote not too long ago covering this topic. So first, where does this name come from? It comes from Tony Hilton Royal Skerm, who by all accounts was a fairly unlucky guy. So here's a picture of him when he was very young. He was hired at age 20 by Rudolf Piles to work at the Manhattan Project in Los Alamos. And so he was one of two British scientists there. But he shared an office with Klaus Fuchs. And I don't know if any of you know who Klaus Fuchs is, but he was essentially a Russian spy who told the Russians how to build a nuclear bomb later. So fortunately, that didn't wreck his career. He went back to the UK, became a high-energy physics theorist, and he came up with modeling baryons, which are essentially protons and neutrons, as topological solitons of a vector field called the pion field. But in the 1960s, high-energy physicists got much more interested in quarks, so this model didn't get much attention at the time. Then about 20 years later, it starts getting some attention, but then string theory detracts everybody, and it doesn't get as much attention as it probably deserved. And then he did receive the huge medal in 1985, which is one of the highest scientific awards in the UK. But he never became a member of the Royal Society because he died shortly thereafter. In fact, he died during a surgery that went unfortunately wrong. So among other things, he didn't witness the role that his model of these topological solitons actually ended up playing in magnetism. So in magnetism, Skermions became a hot topic a little over a decade ago. And this started with this measurement done by a German-Swiss group of neutron scattering on manganese silicon. Manganese silicon was a well-known chiral magnet at the time, where with a phase diagram that was very well established, was shown here. This is the field versus temperature. And you know that at zero field, the magnetization would essentially form a helical phase. Then if you increase the field, it became conical until it became completely saturated in high enough fields. But then close to the magnetic ordering temperature, there was another phase which for a long time wasn't really well known. It was called the A phase, A for being anomalous. But then in 2008-9, this group did some small angle neutron scattering in this A phase regime. And actually, they did some mistake. They mounted the crystal not in the direction that they wanted and what have they. But what happened is they ended up seeing this neutron scattering diffraction pattern that was a six-fold diffraction pattern that was not really commensurate with the crystalline structure. And so it took them a little bit of head scratching to figure out what it was, but ultimately they figured out that this corresponds to a magnetic structure that looks kind of like this, where most of the magnetization is aligned with the applied field, but then you have a periodic array of lines of magnetic flux pointing in the opposite direction. And around those lines...
Axel, sorry, I think it's frozen again.
It's frozen again.
Yes, we are seeing the discovery of magnetic Skermion. Yeah, it was frozen. Yeah.
Right.
Yeah.
Wait, don't hesitate to let me know when I start talking. Should I let you know when I switch slides?
No, I don't think so. But now we are seeing this the slight discovery of magnetism, but we can. Yeah, now it's okay. I think. Yeah.
All right. Cool. Sorry. Maybe the Mac doesn't play well with the software. I don't know. Anyway, so here we have these lattices of Skermions that develop, which have a topologically distinct texture. And you can kind of picture this if you take one of these individual structures and you project the spin structure on a unit sphere by taking the perimeter, bring it to the North Pole, and keep the center at the South Pole, then what you see is that over the whole surface of the sphere, every possible spin direction is represented. So essentially, the spin wraps around once completely around the sphere. And you can describe this by a so-called winding number, which you mathematically can calculate using this integral here. And essentially, that calculates the number of times that the spin wraps the sphere. This is also known as a topological charge. And for these Skermions, it's plus or minus 1, which is different from the conical or field polarized states that are adjacent to this phase. And what we will see is that this topological charge actually has some physical consequences as well. Okay, so now Skermions, it was no accident that the Skermions were observed in manganese silicon, which is a well-known material with chiral exchange interactions. Because the chiral exchange interactions help stabilizing the Skermion formation. In order to understand this, let me briefly discuss what, let me briefly discuss the situation here. So what's written here is the Hamiltonian for simple Heisenberg Hamiltonian that we're all used to, right? You have isotropic exchange interaction, exchange constant J. And if you look at the ground state that you get from this, we know what it is. If J is positive, the ground state is just a ferromagnetic spin texture. Now, if you have a material where inversion symmetry is broken, then besides this symmetric exchange interaction, you can also have an antisymmetric exchange interaction, or Jaruzelski-Maria exchange interaction. So here, the exchange energy is given by the cross product of two adjacent spins, not the dot product. And you can see if you exchange these two spins, if you have inversion symmetry, this term has to vanish. But if you don't have inversion symmetry, this term can exist. And here, the low energy state for the spins is perpendicular to each other. And so if you have both the symmetric and the antisymmetric exchange interaction, then that will give rise to a situation where the magnetization spirals around. It gives rise to these helical spin spirals.
Hello, Axel. Sorry for the interruption, but I think it's frozen from time to time. If you want to proceed, maybe without the full screen, I think it would work.
All right, let me see.
Okay, you can proceed like this, I suppose.
Yeah, so some of the animation, what I can do is when I change slides, I can exit briefly. Maybe that works.
Okay.
All right, so here we have the helical spiral. If you have antisymmetric and symmetric exchange interaction. And now if you also apply a magnetic field, then you can get a Skermion out of this. Essentially, then the helical spirals will overlap and give you these Skermions. Now, as I said, you need this in order to get this Jaruzelski-Maria interaction. And so in manganese silicon, you have this just due to the crystal structure. These are B20 compounds, so these are essentially FCC type structures where you have alternating different layers along the 1-1-1 direction. And just looking at it, you can see how inversion symmetry is broken in these materials. But you can also have this naturally in essentially any magnetic multilayer, because as soon as you have an interface, the interface will break inversion symmetry. So you can have this in like cobalt, platinum, permalloy, tantalum, and all kinds of different layers. This has become one of the main ways how we engineer Jasinski-Maria interactions. All right, so let me see. All right. Now, if we, I mentioned that these magnetic Skermions are characterized by these topological charges, this winding number that describes how the spin is moving around. Now, it turns out this topological charge does have real physical consequences. And essentially, it generates an emergent magnetic field that charge carriers in these materials see when they move around. And so the emergent magnetic field is simply given by the magnetic flux quantum divided by the size of the Skermion, the area of the Skermion. And in a simple picture where the size is determined by just the ratio of the antisymmetric to symmetric exchange interaction, it's just given by the square of this ratio. And this emergent field can be very large. You know, if you have Skermions that are 10 nanometers in size, the effective field is of the order of 100 Tesla. And so one of the consequences is that if you have an electron that moves through such a Skermion texture, it will get deflected by these emergent field, and this gives rise to like a topological Hall effect. But of course, there's also a back action on the Skermion, which then may move the Skermion in response. And so this became of high interest early on because it was observed that if you look at some of these bulk Skermion materials, that the current densities required to move Skermions in these systems is very, very low. It's like 6 to 7 orders of magnitude smaller than what we are typically used to for electrically moving magnetic domain walls. Okay, so this then, there's another aspect of Skermions that makes them interesting for applications where you move magnetic textures. Namely, since the Skermion is a localized magnetic structure, it can easily move around the defect. In fact, as we will see later, due to the dynamics of the Skermion, it likes to move around obstacles even very readily. And this was also observed early on in micromagnetic simulations, where, for example, if you put a notch in a wire, the Skermion will just move around it even at very modest driving forces. So this then suggested that Skermions may be useful for information technologies. There has been this idea that you can use magnetic textures and magnetic wires to store information, very similar to an old-fashioned magnetic tape. This is known as racetrack memory, an idea developed by Stuart Parkin a long time ago. Instead of an old-fashioned magnetic tape, however, you don't move the magnetic material, you just move the magnetization structure within the material by applying currents to it. Now you can do the same thing with Skermions, and you can envision encoding information in the presence or absence of a Skermion. And the beauty is that you can do this potentially at very small scales. And what I think is most interesting, actually, which isn't really captured on this slide, is that you can do it in a two-dimensional way, which allows for much more complex ideas than just these linear kind of devices. Okay, so in order to do this, though, you have to have a way by which you can generate Skermions on demand. And the first step in this direction was done about a decade ago when a group in Hamburg, using a spin-polarized scanning tunneling microscope, showed that by locally injecting a spin-polarized current, they could generate Skermions where there previously were none, and they could also switch it back again. So this is very interesting because now you can think of possibly using the topological charges of the Skermions to encode information instead of using electronic charges as you typically do in information technologies. However, it's not clear that this is really a way how to do this practically. First of all, only a handful of groups in the world know how to do spin polarized scanning tunneling microscopy, and then these measurements were done at very low temperatures, high fields, and it's also not clear whether the Skermions that were created here are actually mobile, because they could only be created at existing defects in the samples. So this is where we came in with our work, where a postdoc at the time in my group created Skermions the same way how his son creates soap bubbles, and that's what I'm showing you next. So, and just in case, there we go. So what we did is we did use films of cobalt iron boron that we sandwiched in between tantalum and tantalum oxide. And so the idea here was that the tantalum gives us strong spin orbit torques and the Jaruzelski-Maria interaction. And the tantalum oxide gives us rise to a perpendicular anisotropy in these films. And you see this if you look at the hysteresis loop as a function of field. The red curve is for the field applied in the film plane. The blue is for the field applied perpendicular. So you see the easy axis is definitely perpendicular to the magnetic films. But we're also very close actually to a spin reorientation transition here in the system. Now we can use magneto-optic Kerr imaging to look at the magnetic structure of these films. And we see that in remnants, we have this labyrinth domain type structure. And if we bias the field one direction or the other, we favor one or the other domain on the expense of the other. So if we now look at this domain evolution with the magnetic field, we can actually look at this domain period and determine the Jaruzelski-Maria interaction quantitatively. Also, what we can do is we can get into a regime where we are in a field regime where we mostly are saturated in one direction and just have isolated stripe domains of the opposite direction. And so then what we can do next is we can go to one of these field regimes here. We have here a sample that we patterned. This is 20 micrometers wide. There's a 3 micrometer wide constriction here. So we have a constriction here that's a little wider than the width of these stripe domains. And by passing a current through this constriction, we can now push one of these stripe domains through here. And when we do this, what we see is that the current will start generating individual Skermions here that pop out at the end of the wire. And you can see we generate a lot of new Skermions that all behave like individual particles. In fact, you see that there are repulsive interactions between them. And as you can see here, I hope you can see this. So, yes? All right. So how do we understand what we see here? Well, there are two ingredients to understand this. One is spin Hall effects, where by passing a current through a non-magnetic layer, we generate a transverse spin current just due to spin orbit coupling in this layer, meaning that spins of opposite directions get preferentially scattered to one side or the other side. And so if you combine our material where these spin Hall effects are strong, such as tantalum, and have it adjacent to a magnetic material, then the spin accumulation that's generated at the edge of these charge current carrying layers can be injected into the adjacent ferromagnetic layer and generate a spin torque. And this is now known as spin orbit torques. Okay. Now, if you combine these spin orbit torques with materials where you have chiral Jaruzelski-Maria interactions, then this results in very efficient torques. Because now what happens is that the spin torque rotates all the spins in the same direction, but all the magnetic structures have a well-defined sense of rotation due to the DMI, and that means you get a well-defined motion of domain walls in these structures. And this was shown, by Jeff Beach's and Stuart Parkin's group quite a while ago. Now, how does that look if we do this in a situation where the current is actually inhomogeneous and where the magnetization structure is more inhomogeneous? So if we have, instead of a thin wire like here, where we have a domain wall all across the wire, an extended magnetic film with a stripe domain, it's important to notice that the spin torque only is very strong in this case when the magnetization is collinear with the electric current direction. And so that means if you look at these stripe domains, there's only spin torques acting on the tip of the stripe domain, but not on the side walls. And if you put now this stripe domain into a constriction where you thereafter have like an inhomogeneous current distribution, then this will mean that now you also generate forces on the side walls of this domain structure. You start blowing up this tip, and then you get like a necking instability at some point where you just disconnect a domain from this structure. This is a little bit like a Rayleigh-Taylor instability that you have in surface tension-driven fluid flows. And so this is schematically the mechanism by which we see this Skermion formation here. And in quite general, it turns out that inhomogeneities in your material, it doesn't have to be just current density, it can also be magnetic inhomogeneities, can easily seed Skermion formation through electric applications of electric currents. So we looked at this via micromagnetic simulations. Now we used material parameters that were very similar to what we measured in our samples, which makes it hard for the micromagnetic simulations because it also means that the domain structures are very large scale. So it's so large that we cannot make the simulation large enough to contain the full stripe domain. So you only see like the tip of the domain wall here. But if I now start the simulation or the movie from the simulation, we see that this domain wall moves out and then it becomes very complicated. But ultimately, you see that there are Skermions formed. And when we switch off the current, this domain wall recedes here and we have an isolated Skermion that formed essentially described to you. But then we went and did the simulation also at much higher current densities. And now the spin torques are so high that they actually destroy the domain wall and pull the magnetization to be completely in plane while the current is applied. And this is the picture of the micromagnetic simulation while the current is applied. And if we switch off now the current, we see that again we can form Skermions, essentially condensing out of this saturated magnetization state. And so this formation process is actually very different from this other one. It's more like a Kipple-Zurich kind of formation process where you have some inhomogeneities in the phase transition, if you want so. But it showed that there can be two rather distinct mechanisms for Skermion generation. One where you deform an existing domain structure, another one where you just create it out of nothing, if you want so. And so we're going to try this experimentally. And so in order to do that, we took our tri-layer structure, we got rid of the magnetic contact in between and replaced it with a high conducting non-magnetic contact. So now there's no magnetization structure that gets transferred from one side to the other. We reduce heat by making this very thick. So we only have this divergence of the current here. What we did see is that in order to generate Skermions, we required larger currents. So here you see a movie. Instead of a DC current, we just use current pulses. And you see with almost each pulse, we generate new Skermions here, even without having an initially reverse magnetic structure to begin with. So now that we know how to generate Skermions very efficiently, we can think about studying their properties a little bit more carefully. And so in particular, what we were interested in was the Skermion Hall effect. I'm sure most of you are familiar with the classical Hall effect, where you get a transverse electric field from electric charges moving in the presence of a magnetic field. Essentially, the Lorentz force gives rise to a force that's perpendicular to the velocity. Now, it turns out if you have a moving object, there's a similar force at work called the Magnus force. And what we will see is that for Skermions, we get a transverse force due to their motion, which is very similar to this Magnus force that you get from rotating object. And so here the displacement, the transverse displacement, is directly correlated with the topological charge. And I wanted to demonstrate this with a simple example. So I hope you don't mind demonstrating this with the help of a Brazilian expert, who's Roberto Carlos. He shows here, with the help of some French collaborators, how to move an object using its rotation on a curved trajectory. So he wants to move this object from here to there. And as you can see here, this very easily works by having the ball spinning very quickly. Now, you may wonder, excuse me, so what has in common with a moving soccer ball, right? Well, what they have in common is the following. When we move a Skermion in a material, of course, we don't move all the spins. What we do is we rotate individual spins so that the magnetic structure in response moves through the material. And so if you look very careful, then you see if you want to move the Skermion from the left to the right, then on the top half of the Skermion, the in-plane spins have to rotate counterclockwise, while the lower half of the Skermion, the spins have to rotate clockwise in order to make the whole structure move. Now, there's a different sense of rotation then. And so what that means that locally for those spins, it looks like they're exposed to opposite magnetic fields, which makes them precess in different directions. And so essentially there's an effective field gradient of the Skermion, and this field gradient can then couple to the magnetization in the center. And we know what happens if you have a magnetization in the field gradient. It results in a force, and so this force pushes the Skermion in a transverse direction. And you can actually see this in the micromagnetic simulation. If you put a Skermion at the center of your wire here, and then apply a force that tends to push the Skermion towards the right, it actually will initially move upwards, or mostly upwards, until it gets repelled from the boundary. at which stage it starts moving more and more in the direction of the actual current here. And you can describe the forces acting or the motion of a skyrmion by using the so-called Taylor equation. You get the Taylor equation by taking a rigid skyrmion spin texture, plugging it into the Landau-Lifshitz-Gilbert equation, and the resulting equation that you get is the following. It has three terms. This one here is the driving term, which describes the force on the skyrmion due to the electric charge. Then you have a dissipative term, which is given by the magnetic damping, geometric factor, and the velocity of the skyrmion. And then there is a gyrotropic term, which is given by the topological charge. And the cross product of the topological charge essentially with the velocity here. So that is what gives rise to the force that's perpendicular. And you can, from this model, easily estimate what should be the ratio of transverse to longitudinal velocity. And it's simply given by 1 over the magnetic damping and this geometric factor d. Now, we can see this even in the experiment. So what I'm showing you here now is a mock imaging of a wire where we apply a homogeneous current. And as you can see, we have individual skyrmions that do move at an angle with this current. And we can, we can look at this in more detail. I showed you that the transverse motion depends on the topological charge. We can actually reverse the topological charge by reversing the magnetic moment because the topological charge is odd in the magnetization. So as you can see here, here are two pictures, two movies for skyrmions with opposite magnetization. And indeed, one of them moves downwards, the other one moves upwards. And so the way how these movies are done is they are done with current pulses. So we can look after each current pulse, what is the displacement in X and Y. And you see in these situations where we have this clear defined angle of motion, we get essentially always the same displacement in X and Y with each current pulse, which means that we are in what's known as the Skermion flow regime. Now, if we reduce the current to very small currents, then we see the situation is actually different. Now, Skermions just mostly move in the direction of the current and have some random motion up and down. So if you look careful, actually, you see now that with each current pulse, there's much more variation in terms in motion in X and Y. And so now we are in a regime where the motion is much more determined by the defects in the materials. And so that's why the dynamics is quite different. So so this is summarized here. So what I'm showing you here is the Skermion Hall angle, which is essentially the direction of the Skermion motion with respect to the applied current as a function of current and for various different applied fields. So this is for positive applied fields, this is for negative applied fields. And you see that the angle is opposite for the two fields, which makes sense with respect to what we thought about the topological charge. So also you can see that this angle gradually increases until it saturates at high enough driving force, right? So What that means is that we slowly get from this dissipation-dominated regime into the flow regime for the Skermions, where dissipation then doesn't matter anymore. So in this regime, we can now compare what we expect to our simple estimate, where we estimated that the ratio of the velocities should be given by 1 over alpha and d. So alpha in our samples is about 0.002, and d is essentially given by the ratio of the size of the domain Skermion over the domain wall of the Skermion. So in our case, our Skermion size is roughly 1 micrometers, and the domain walls we estimate to be more of the order of 10 nanometers. And so this ratio D becomes about 60. If you plug these numbers in, we expect 0.83 for this ratio, which corresponds to an angle of 40 degrees. Experimentally, we measure something like 30 degrees, which is not bad considering the uncertainties in some of the values that we have. More importantly, what you see is when we change the applied field from 4.8 to 5.4 Ørsted, we see that this angle becomes bigger. And what happens is as we increase the field, the Skermions actually become smaller. And you see, since D is in the denominator here and becomes smaller for smaller Skermions, we do expect a larger angle with a decreasing diameter. So it turns out that you expect to see a similar behavior even in numerical simulations where you look at the influence of disorder in the system. So again, here you expect a Skermion Hall angle that's linear in the driving force, and that saturates when the driving force becomes comparable to the pinning force. So you get to this flow regime at high enough forces for the motion. Oh man! So one more thing that I wanted to say. If we look at the interior of the sample, we see indeed this very well-defined motion of the sample there. Now, from our simulations, we expected that as we get closer to the edge, that due to the repulsive force from the edge, there should be actually a higher velocity. But what we see is that now, close to the edge, the trajectory becomes very complicated again for similar what we think is happening is that when you get closer to the edge, you have a higher density of defects. Especially, remember that the way how this movie is, it's shots after individual pulses. So during the motion, the Skermion is probably even closer to the edge. And so that's, we think, is when you're close to the edge for the same current density, you're still not in this flow regime, and that's why the velocities are not as high as we would expect them to be. So this brings me pretty much to the end. So what I've shown you is that we can generate Skermions in various structures, that we can move them around electrically, we can generate them electrically. So you can think of putting them into complex structures like this, for example, and then if you pass a current through it, you see how the Skermions can move. This looks almost a little bit like a racetrack, although a very bad one, because as you can see, the motion is rather stochastic, so you scramble any information that's in the position with the Skermions really fast. But you can have a lot of fun understanding some of the dynamics of these Skermions in more detail. Now, this work was really done mostly before I came to the University of Illinois. This was done at Argonne, where this is the group that did the work at the time. In particular, this guy here at the center, Wanjun Zhang, he was the driving force for most of what I've shown you today. He's now a professor at Tsinghua University. So here's now a list of all the people. Wanjun Zhang was the main player. There were other postdocs, Wei Zhang, Benjamin Jungfleisch, who contributed. A lot of more senior people, John Pearson, Frank Freyden. Ola Heinenen did the micromagnetic simulations I showed. And Susanne Feldhaus was instrumental in all the MOOC imaging and so on. We got the samples from Kang Wang's group at UCLA, and Jaroslav Tsakovniak and Prami Upadhyaya helped us a little bit with the theoretical understanding. Zixiao Zhang and Yang Zhu did additional micromagnetic simulations, especially related to the Skermion Hall effect. And Zhao Wang, who was a student in Jumei Cheng's group at Weimar College, helped us with the measurements for the spin Hall effect. And I gratefully acknowledge support from DOE. So this brings me to the conclusion. I showed you how you can have magnetic Skermions in magnetic multilayers, that you can use interfacial interactions to stabilize them at room temperature. I showed you specifically for tantalum cobalt iron boron tantalum oxide layers, how we can electrically generate Skermions in two different ways, by deforming domain wall structures or by just creating them out of nothing. Besides being able to generate Skermions, this may actually also be an interesting model system for studying instabilities in complex flow regimes. And then at the end, I showed you how the topology of the Skermions influence their motions, and how we see this current-dependent Skermion Hall angle when we drive them. So that's the end. I'll be happy to discuss any questions, and I apologize for the technical difficulties. I hope it was.
Okay, thank you, Axel. Thank you, Axel, for this wonderful talk. At the end, it was solved, I think, the technical issues, but yeah, we could hear properly. So I would like to open the session to questions. Okay, we have one question from Alejandro Colton. Please go ahead.
Yeah. Yes, okay, thank you very much for the talk, very nice, I enjoyed it. I'm very curious about the behavior of the Hall angle, the picture you show in the conclusion. There is like the pinning transition of the Hall angle, right? I mean, for a very small current, you have zero. I imagine that this is the average Hall angle, right? That is zero. I wonder, in that regime, I mean, you have transverse fluctuations which are bounded, or they are not bounded. The Skermions just diffuse transversely with an average zero Hall angle. Is that the case?
Yeah, so you're absolutely right. I mean, the Hall angle is, of course, average quantity, right? So we got this from the trajectory over several pulses. And yes, so this is very similar to what you're familiar with maybe from vortex physics in superconductors.
Sorry, Axel, we lost you for a minute. Could you please repeat your answer?
Oh, okay, sure. So you're absolutely right. The Hall angle that I'm showing is an average that comes from several current pulses. And you're also right that this is like a de-pinning type of transition, right? It's very similar to what you see in vortex type physics in superconductors, where upon stronger and stronger drive, you go from a diffusive kind of transport to this flow type of transport. So does that answer your question?
Yes, so it's like a channeling effect, but it's an effect of an individual Skermion, right? That channels through the pinning landscape or something like that.
Yeah, no, I don't think it's channeling. I don't think there are specific channels, because I mean the way how I think about it is that the pinning landscape is really very random.
Yes.
It's just the randomness of it that it, in the low current regime, your Skermion really just hops from one pinning center to the next. And yes, as you've seen in the experiments, they were done in a regime where we really look at individual Skermions. So we can, this is different from like the numerical simulations that I showed, which were in a much higher density regime. But
Okay. Okay. Thank you.
sure.
Thanks, Alejandro, for your question. I do have another question. In slide 20, I think you mentioned that magnetization goes in plane when you have high current. This is because of the torque, I suppose, that the texture is feeling, maybe?
Yes. So you're talking about this. That
Yeah.
is correct. So if you look at the spin orbit torque, the spin accumulation is in the plane. And it turns out at high enough current, the any orienting into the plane. Now, do we see this experimentally? Not necessarily. So first of all, remember the simulation is on a much smaller scale than the actual experiment, right? So meaning that in the actual experiment, very quickly the current density becomes low enough that we don't see this. But close to the contact, I do imagine that we disturb the magnetization structure quite significantly. It would be nice to look at this like time resolved in some greater details. But we do also, when we look at these structures, let me see, at these structures here, I said there's no heat involved. It's not quite true. I mean, there's still a little bit of heat involved, so that's why we use our short pulses, right? So we couldn't do this in a DC fashion. We would ultimately.
Okay. Now that you are in that slide, I would like to ask, do you need to anneal your sample for the cobalt iron boron get some out of plane magnetization, or is at room temperature?
No, so this is at room temperature. So
but what I mean is, if during the fabrication of the sample, you have only 1 nanometer of cobalt iron boron, do you need to anneal the sample post fabrication to induce the PMA?
No, we don't need to do that. So I think your question is related to what you typically do when you want to do an MgO-based tunnel junction, right? So there, what you do is you start with the cobalt iron boron, and then you anneal the cobalt iron boron so that the boron diffuses out and the cobalt iron actually crystallizes. And you want that in order to get the high tunnel magnetoresistance across the MgO. You do have the perpendicular anisotropy just by having the oxygen there. So we want to keep the cobalt iron boron amorphous. That is actually key to being able to see the dynamics as it is, because that's what gives rise to the rather low pinning, and which allows us to see the dynamics of these Skermions very well, including also the Skermion Hall angle in the flow regime, right? So no, we want to stay away from annealing for sure.
Okay, thanks. Is there any other question? Please, Alejandro, go ahead. You're muted. Ale Colton, you are muted if you want to ask.
Sorry, no,
Okay.
sorry for. No, I was wondering about the application of Skermions, in especially in narrow tracks, right? You mentioned that Skermions are good because they avoid effects, but I imagine that as you reduce the track, I mean they will not be able to avoid all these effects, right? So disorder effects might be maybe stronger and stronger as you reduce these channels, no, these racetracks. So how predictable is the motion of a Skermion in a very narrow track?
Well, so a very good question. So first of all, I think while I did say that a lot of the work was motivated by this idea of can we use Skermions for racetrack memories, ultimately I think this is probably not the best application for them. It turns out, if you really want to move them fast, you do need to apply high currents. And the high currents, you have to worry about then the stability of the Skermions and all that. So there are all kind of issues along those regimes. But I do think where Skermions are potentially much more interesting for is if you use larger arrays where you have a potential two-dimensional motion of the Skermion, and where you can even make use of some of the stochasticity. So there are some ideas how the stochastic properties of the Skermion motion may actually be useful as a source of entropy for probabilistic type of computing. So that I think is most interesting. The other thing that I think is interesting is that once you have a complicated arrangement of Skermions, they individually also have dynamic excitations, like breathing excitations, when they grow and shrink. And the frequencies of these excitations is very much determined by the interactions of the Skermions with other Skermions. How far are they away from other Skermions? So that means that you get a direct picture of the real space distribution of Skermions by looking at the frequency dependence of their excitations. And so again, I think that becomes an interesting in that you can encode a lot of information in some more complicated arrangement of Skermions that you then possibly can read out due to their dynamic excitations. So those are the things that I think are possibly much more interesting. None of those are really that close to a real application at this point, I would say. So that's still fairly elusive.
Okay, thank you.
Sure.
Thank you, Ale, again for your question. Carlos, I think Carlos has a question now.
Yeah, thank you, Axel, for a beautiful talk. I'm sorry that sometimes we had some problems of hearing you. You have beautiful.
I have problems sometimes too. So
Yeah, we hear a bird all the time, which is outside your window probably, but it's a very nice bird, sung all the time. And now the picture you have there, I'm surprised how neat are the images. Is that done only with 1.1 cobalt iron boron film, or you have a jig on top that reveals the no
this is just the cobalt iron boron. I mean, so the cobalt has a strong K effect, so that helps. Anything with cobalt is a good starting point.
Okay. Well, thank you very much.
You're welcome. That was easy.
Good. If there is no another question, I would like to thank you, Axel, again for your talk. It was a very beautiful talk. So, and thank you for sharing your work with us. Hopefully, we are looking forward to see you here in November for the Spin Argentina. Yeah.
Yes.
Please share the information of the workshop with the people of your group, so they can send their abstracts.
Yeah.
Okay.
I'll do so. Definitely. Thanks again, and I'll definitely look forward to seeing you all in November. And I'll tell you a different story with less technical problems, I hope.
Yeah.
Thank you.
Okay, thank you, Axel. And with this, I will finish this new seminar. So see you again next week. Thank you.
Bye.
Bye-bye.
Bye-bye.